Okay, that's enough time. Hopefully you were able to make a start on it, but I'm gonna show you guys how to do it really quick. Let's go. Okay, go away. So I'm gonna go ahead and open. Let's see, how do I want to do this? I'm gonna do this in my terminal because I just feel like being cool like that today. So let me get rid of these. Go away. Okay. So let's just quickly calculate this error. So I'm gonna import NumPy here, and then I think this is the only thing that I need. So let me make my data points. Okay, so first let's get our points in here, then we'll worry about the line later. So let me make my y's. I'm gonna call them y obs. Obs means like observed to keep it separate from the actual model line. And then I'm gonna make that an array. 0, 15, 27, 13, 18. Okay. And then I need to figure out for each of these like scattered x values, what the value of this line would be at that point. So given this equation, we can quickly just define a function to figure that out for us. Or I can also use the power of NumPy, which we showed you guys a few weeks ago to make that a little bit easier. So I'm going to make this other array called x observed. I'm going to fill that with the x values. And then I'm going to transform this array into those model y points. So I have the equation, which is, I'm going to call these x expected. Expected is for the line. And take x observed, multiply that by 10, and then add 3. And this is super easy to do with NumPy because everything is element by element. So if I check out what x expected looks like, those are going to be all of my, these are all of my y values for the points on this line at these x values. So now that I have those points, now I can actually calculate the error between these. So we'll use this formula, and we're going to talk about that in like a second if you don't recognize it. So manually, we know that n is going to be 5. So 1/5 times, and then the little summation symbol, and then the difference squared. So let's start with sum. The nice thing about these equations is that they translate very literally to the Python code. So the summation just turns into the sum, and then we will take the y observed, subtract the y expected, square that, and then close the parentheses. And then let's see if this works. Nope. Oh, because I named this the wrong thing. Let me fix this. So this should be y expected, but I named it x expected, which is wrong, but it's okay. We'll just fix that. Okay, this is what I got. Did anyone get something different? I totally may have messed it up. Looks good? Okay. Any questions about this? Yeah.
Is there a way to do turning like that entire data set into like a
Like a 2D array of x and y? You totally could. And then you use slicing to extract the x and the y. I kept them separate just because I think at the end you only need the y components, and I think having the x makes it a little bit messy, but totally would work. Any other questions? Are we gonna move on? Okay. All right. So let's talk about the like most basic types of error that you're gonna run into. So root mean squared error, super common. I think most of you have heard of this one, but it stands for root mean squared error. The nice thing about these two errors is that the name literally tells you how to calculate it, which is very convenient. So root mean squared error, here's the squared error, the error squared. You take the mean, so you sum all of them up, divide by the number of points, and then you take the square root. Wow, so nice. Outside the inside root mean squared error. And then the mean squared error is this without the square root. So you take the error, you square it, you take the mean, and then you're done. So I remember when I first learned mean squared error, I was like, oh my God, that's so useless. Why do we need both? Like they're both the same thing. But actually mean squared error ends up being a lot more significant in fields like statistics because it's also called variance, which we will also run into later. So don't forget about this one, even though this is the one that you'll probably be using more often. The nice thing about both of these errors is that because they're basically the same thing, minimizing like root mean squared error by default minimizes the mean squared error as well. So that's a concept that you might end up taking advantage of later. Any questions about these formulas before we move on? Okay. Let's talk about chi-squared really quick. Um, chi-squared, there's a lot of different types of chi-squared formulas. This is the one for quantitative data. I remember running into the one for categorical data back in high school. So they're distinct different equations. So this one is kind of what we did before. So you take the equation outputs, just like the expected values, versus the actual literal point at that value, so the observed, and then you divide it by the error at that point. So in my previous toy example was just the table. There wasn't an error at that point. This is like a separate value, and then you square it, and then you sum all of them up, and that's what that value is. So there's also like a different version of this. This reduced chi-squared, where you add in the number of points and the degrees of freedom. The degrees of freedom is the number of fitted parameters. So in this case, that would be the number of variables in the equation you're fitting to it. So if it's a straight line, that would have 2 degrees of freedom because there's 2 parameters that you can change. You can change the slope and then the y-intercept. That was super fast, but we're not going to use this a whole lot on this class, but you'll definitely see it later. So hopefully when you see it later, you will remember that you saw it before. Okay, let's talk about the packages that we're going to use to do these types of problems. We have NumPy.polyfit. This one is pretty convenient and it's really nice for just doing polynomial fittings. So straight lines, parabolas, it got so dark in here all of a sudden, quadratics, cubics, all that stuff. If you want to do any other type of equation, like we saw the sigmoid earlier, SciPy.optimize at curve fit can do any equation you want. Not just polynomials, you can do weird stuff like sigmoids and just like really bizarre crap. So if you want weird functions, SciPy.optimize at curve fit, and then we're going to focus on using that one because I know how to use it better. But NumPy.polyfit is super easy to use as well. And I think you can figure that one out by yourself. But this one, hard to figure out by yourself, so we're going to walk through it. Let's do a really quick demo. So go open up like a Jupyter notebook, and then we'll start cooking a simple example. Time to wake up. It's so dark in here. Okay, did everyone get this open? Like, are we good to keep going? Okay. So this will be a super simple example of just fitting a straight line to some data. But we're gonna like walk through it. We're gonna make the data. We're gonna fit the line. It's gonna be great. My arm feels so short without the stick. So let's import our packages. Let's see. If you remember our plotting package, we're gonna pull that up. So this is too small. That's probably too big. And then this is the new package that I just talked about. So it's called scipy.optimize. And we're going to give that an alias just because scipy.optimize is kind of long. And I personally don't want to type all that out every time. Okay, raise your hand if you finished that. Okay, almost everyone. Wait like 10 more seconds. I don't want to move on until we're all like done with importing the packages. Okay, no more typing, so I think we're done. Let's go ahead and make a little toy data set. So we're going to start by just I want the data to be kind of in a straight line form because we're going to fit a straight line to it. So this next cell is just going to be like me forcing a noisy straight line scatter plot. So if I want to make any straight line, I need to give it a slope and an intercept. So for slope, I'm going to do like 1/2 because I feel like it. And then for the intercept, I'm going to say, someone pick a number between 1 and 10. 7? 7. Mm. Gonna set this extra parameter called sigma equals 1. I'll talk about this in like a second. Can you guys see the screen? Okay, like turn on the lights. Okay. So sigma equals 1, and then I'll talk about that in like 2 more lines. And then I want the number of points I want is do 20. And then let's give myself just some range of x values to make my fake y values for. So I'm gonna call these like x data. And then I'm just gonna actually I need numpy. So import that too, sorry about that. And then make myself some points between let's just do 0 to 10. Okay, so there's a problem with this. Does anyone know what it is? There's like there's no like logical issue, but in terms of like what I'm trying to do, there's something wrong. Any ideas? It's in the last 2 lines. Okay, so how many points will this NP.A range make? Right, and then I said I want 20 points, right?
Oh,
So that won't work. Let's fix that. What function would help me make 20 points in the interval 0 to 10? It's a NumPy function. Yeah, linspace. 20. I think that works. I don't remember the syntax for linspace, but it looks okay. And then let's generate our fake fun y values. So I'm gonna call these y data. And let's start with the y equals mx plus b. So we have our slope, which is m, times all of our y values, sorry, all of our x values. And then we're gonna add the intercept. So this is just the basic linear equation. But I want to make them noisy. Like if they're all already in a straight line, what do I need a curve fit for? So let's make them a little bit fun. I don't know if that's the right word, but we're gonna make them noisy. So this is our equation, this whole like m times x data plus b, but you don't need to add the parentheses, this is just for like clarity. And we're gonna add some noise to every single point. We're gonna add random noise. So if they're all in a line, we're gonna go and like flick them up or down by like some random amount. So the way that we can easily generate just a simple noise value is by using a NumPy function called random.standardNormal. And then this will generate random noise according to the Gaussian bell distribution. That's like a little bit out of scope, but it's going to give us random noise so we can go ahead and flick those points up and down the line. And then I want 1 random noise value per data point. And then multiply this by sigma. In this case, sigma is 1, so this won't really do anything. But if I wanted to give my points any value of noise that is like more than the usual values they'll see in the standard normal, you can make sigma like 5. And then they'll give you like a lot of noise because the standard normal is the average is 0 and standard deviation is 1. So this usually gives you really small numbers. Like if I wanted huge numbers, I would make this like 10. But I'm not going to do that. Okay. So these are our little toy points. Let's go and plot those. Go ahead and like give me a thumbs up when you're like done with the setup and the plotting. Just like put it over here. Okay, we got like half the people done. Yeah.
I just had a question, like, so what does, like, how does it make it, how does it add the noise, the random standard normal?
Yeah, so the random standard normal,
Like, what does the size parameter?
the size, okay, so NP random standard not normal will give me back points. It'll give me back numbers that are randomly sampled from the normal 0, 1. So average 0, standard deviation 1. So like the very specific bell curve. The size equals n means I want n numbers back. So because I'm getting back, let's see, so n is 20. So this is giving me back an array of 20 random noise values. And then I add those to the y values.
Size of the.
Yeah.
Okay. And
So
then
I get 1 per.
what does sigma do?
Sigma is just like sort of like a magnitude value. So if I wanted more noise, then I would go bump this up. Since it's 1, it's like kind of there for fun, but
So then all of the numbers in that array will be less than or equal to 1.
in here.
Yeah.
So these are, again, these are selected from the standard normal, which is a range of values. It goes from negative infinity to infinity. Most of the numbers are between -1 and 1. But let's, okay, so if I bump this up to like 10, this is a lot of noise. If I bring it to like 0.5, a lot less noise. So that's what sigma does. And put it back to 1. Okay, I'm gonna move on. So this was us making data, which is like kind of boring or whatever. So let's actually do the thing that I just talked about, which is fitting the curve to this. So the first step in running SciPy's curve fit function is defining your equation. You have to do this a very specific way, and you'll have to do it on your homework and also for your final projects. I think you have to do curve fitting. So this part is super important, so if you mess it up, it won't work. So this is how you do it. We define a function like we would any other function. We give it a name. I'm gonna call mine F because I love creative names. And the arguments have to go in a very specific order for SciPy's curve fit function. So you start with X, always. First argument has to be X or some proxy for X. You've got like X value, but it has to be something related to X. Then after that, we can give it our equation parameters. So in this case, we're doing a straight line because I'm looking at this and I'm like, ah, that looks straight. So the parameters for a straight line, I know that the equation is y equals mx plus b. And in that equation, m and b are the parameters. So if I vary m and b, I can generate any straight line that I want in the world. So those are my two parameters. M, b. If we're going to do like a quadratic equation, it's like ax squared plus bx plus c. So I can vary 3 things. I can vary a, b, and c. So those would come after x. It'd be f, x, a, b, c. And then what we're going to return is like the most simple thing possible. We're just going to return m times x plus b. So you return how you want to transform the x value. And in this case, we're just doing a straight line. So it just looks like that. Okay, so the next thing you have to give SciPy's curve fit function is, actually, I'm gonna wait for you guys to finish this. We'll move on. Okay, there's less typing, so I'm gonna move on. So the next thing you have to give it is called like, I call it P0, but it's basically just your initial guess at the parameters. This might seem like super useless because it's like I'm giving it the equation and I'm also telling it where to start. Like, does that mean I already have to know what the equation is? And the answer is no. For polynomials, SciPy's curve fit is like super good, and your initial guess of the parameters can be like super off, and it'll still get it. For more complex functions, you do have to kind of tell it where to start, because let's say you have like a really super high period trig function. It's like, it looks like this, and you have to kind of tell SciPy that like it has a really tight period, or it'll like try and fit really wide period functions to it, and it will never get there. So in some cases, it is helpful. You do not need to really know what the values are, but telling it where to start is like super helpful. Again, less helpful for polynomials. So in this case, we can kind of give it whatever we want. So I'm gonna call it P0. You can call it anything. And then I have to give it one guess for each parameter in this function. So I need to give it one guess for kind of what I think M is gonna be, and then sort of what I think B is gonna be. So let's just say, pretend like you don't know. Like, I know we made the data, but like pretend like you've never seen it before in your life. and someone just gave this to you and you're like, oh my God, I think the slope is 1. And I think the intercept is like 5, 7, 7. Yeah. Okay, so that's my guess. Because I'm literally just guessing. And our next step is going to be to actually call the function. So this function actually returns 2 things. It returns a tuple, and we're going to just unpack that as soon as it comes out. So these are the 2 things that it returns. When it returns them, I'm just going to split them up immediately into these 2 variables. So the first element in the tuple that it returns is going to get assigned to parameters, and then the second thing that it returns will get assigned to covariance. And we'll talk about what the covariance is later. Actually, this is the covariance matrix, so I'll rename it. Again, we'll talk about that in a second. So actually calling the function, so we rename that library fit. So fit.curveFit. And then we're going to give it all that stuff we just made. So the first argument is the function, the model equation that we defined that I called f. So give that f. And then I need to give it the x and y data, the observed values. So I have x data and y data. And then I need to give it my initial guess. So that's p0, and that's the last argument. And then if I run this, hopefully it won't yell at me. Let's see. Okay, great. Yeah, it ran. So try and run yours, and hopefully it'll work. I'll give you guys like a minute to like get all this down. Yeah.
No, it's fine. My scatter plot is to show this, please.
Any other problems with getting any of your stuff working, like the plot, the function is running? Okay. Let's look at these outputs then. So what does parameters look like? So this is an array of 2 values, which is good because I gave it 2 things I wanted it to give back to me. So this first one is what it calculated as the slope of the line that it generated, and this is going to be the intercept. And I know the order of those because they're going to be returned in the same order that I listed them in this function. So if let's say I put x, then I put b, and then m, because the order of the parameters in the model equation actually does not matter. Then this one would be the slope, and this one would be b, and this would be m, because that would have been the order in here. But in this case, I give it m first, so that's the first thing that comes back out. Slope intercept. Let's look at the covariance matrix too. So this is a 2x2. And what this is basically a measure of how, so it's 2x2 because we have 2 parameters. And this is a measure of how those parameters sort of vary with respect to each other. So if we can pretend like this first row is like, this first column is like the M column, and then this is the B column, and then this is the M row, and then this is the B row. Then this element would be how M varies with M. And that might sound kind of insane, but that is actually a variance. The covariance of M with itself is its variance, and the covariance of M with B is the covariance of M with B. So we're going to ignore these. It is symmetric, this is gonna be how B varies with itself, because this is the B column and the B row. So this is gonna be the variance of B. And we're gonna use these later because these are the variances of these parameters, we can kind of use this as a proxy for error. And this has some limitations because it does assume some things about the underlying distribution, like we gave our plot random noise. And this does assume that that noise is normally distributed. In our case, it is because I gave it that on purpose. But if it isn't, always have to look out for your assumptions. And this covariance matrix does make some assumptions. So in the meantime, we have our variances for each parameter, and we can use that as kind of a proxy for error. So let's go like and extract those really quick. So my slope error is going to be the first row and first column. So that will just be 0, 0. And then my B error, sorry. Let me do that correctly. And my B error will be like basically the same thing, but first row, first column. And then let's go ahead and pull out our parameters too while we're at it. So we know that our M, like for the predicted equation, is going to be the first value in parameters. And then our B prediction will be the second value. And then I'm just going to print out the values for M so we can take a look. And then I'm just going to stop there for now so we can move on. So this is our error. Where's my stick? This is our error for slope, and this is our guess for slope. There's one more step that we always want to do. Yeah.
So in the covariance matrix,
Mm.
0, 0, and 1, 1 is the variance for that like variable, like the one from the other equation?
Yeah.
Okay.
And as we know, variance is mean squared error. So if we go ahead and square root that, we'll get the root mean squared error proxy for that parameter. Yeah. Oh yeah, I should have renamed this. Yeah, sorry about that. The errors for the variances for the parameters are always along the diagonal. And I should have renamed that and I didn't, so that's my bad. Okay, there's one last step you want to do with this that you always want to do for curve fitting when you can, is to plot your original data with the generated line. Just make sure that they make sense, because sometimes they will not, and then you'll have to like redo your fitting. So let's go ahead and do that, just to make sure that it's all good. So like we did for the little toy air example, we had to calculate all of the line values for those X points. So let's make so we have an equation, right? We have M and B, and we need to apply that equation to a bunch of X values so you can see what it looks like. So I'm gonna make another lens space. And because I know that my original X values are from 0 to 10, I'm just gonna do 0 to 10. And then I'm gonna give it 100 points because I feel like it. I feel very powerful and I feel like doing 100 points. Should I do more? I'll do 150 points just because I feel crazy. And then we already have our little model equation for y, so I'm going to reuse that. I'm going to give it my x values. I'm going to give it the slope that I already pulled out. I'm going to give it the intercept that I also pulled out. So this is like the equivalent of me like applying that 10x plus 3 function to those x values, except that I'm just doing it for a bunch of x values within the interval because it's just matching up the line to the graph. It doesn't matter that I do it to the original x points or not. Okay, let's make our graph. Figure sandwich. So figure, plot, spread in y. I'm gonna put the original scatter plot of x data and y data, and then I'm gonna show it. So once all that is done, you should have, mine is cut off, but it doesn't matter. You should have both the scatter points and then the line. And just from the part that I can see right now, they look like they align pretty well. And yours should also align pretty well. Any questions about like this process or like any of it? Yeah. The 0 and the 10?
Yeah.
Okay, so lint space, I guess, I don't know if all of you guys have used it, but lint space takes 3 arguments. Let me make this lower so I can reach it. This first value is, so the first and second values are the start and end values of an interval. And lint space is a little bit different because it does include the end value. So unlike list slicing, the 10 will be included. And then the 150, so the third value is how many intervals I want to chop that into. So 0 to 10 is my interval, and then 150 means I want 150 slices of it. So this will give me back 150 points between 0 and 10, including 0 and 10. Any other questions? Yep. I'll like upload this notebook to B courses after lecture too. Any other questions before we move on? Yeah.
If you wanted to do a function that isn't aligned, you would just change like whatever app is.
Yeah, you change it. And then you'd have to adjust the plot at the end too.
And what was it? The function could do any curve?
Yeah, you can do anything. You can put in like E. It's fine. I think I tried to fit like a harmonic oscillator curve and it worked. It took a long time to fit it, but yeah, like anything. Which is why it's nicer. It can be nice. NumPy.polyfit only does polynomials. But again, this can do anything. But the weirder your equation gets, the more you have to work on your initial guess. So like if you try to fit like a harmonic oscillator to it and you don't give it good initial guesses, it'll probably never be able to fit anything. So you should also have an understanding of what equation you're putting in. Otherwise, you're going to be a little bit stuck. Okay, am I good to move on? This is the end of the demo. So I'm just gonna be like yapping at you for the rest of the 10 minutes. Okay. Go away. Okay, it's time for more math. Sorry, guys. Let's talk about linear regression. So linear regression is just a special case of curve fitting. We actually just did it. We just did linear regression. Congratulations. Oh my God. You basically just only fit a straight line. And by manner of their construction, linear regression equations minimize the error just by default. That's just how they work. There's like some statistical backing for this that is like super out of scope. We're not going to cover it. But if you want to read about it, I think it's covered in Data 140. I think it's covered in Stat 134. So you can check that out. Let's just talk about R and R squared really quick. So R is called the correlation coefficient. It measures basically what the spread of the data set is. I'm sure you guys have run into this before, but it ranges from -1 to 1, where the sign of R correlates to if it's a positive or negative slope. For values of R and how to interpret it, the closer the absolute value of R is to 1, the closer the points are to just lying exactly on a line. So if we think back to our original data set, or not the toy data set that we plotted, and that sigma value, so the more I bump up sigma, the more noise we get, and then the smaller R is going to be. So if R is super close to 0, the absolute value, regardless of sign, it means that there's a really weak linear correlation. An important thing to remember about R and R squared is that these only measure the strength of a linear relationship. So you could have like a really beautiful parabola and R will be really close to 0 because it's not a line. So just because R is really close to 0, always plot your data, make sure you know what it looks like, because just because R is 0 doesn't mean there's no association. It just means there's no linear association. So yes, this is what I said before. So both of these have 0 correlation. This is, obviously this has a shape. It's a parabola. This would be really easy to fit a line to, just not a straight line. The straight line would go like straight across horizontally. So there's no linear relationship. And then this is just a cloud. How would you fit anything to this? There's nothing. So this is why it's always important to plot your data, because without plotting it, it's hard to tell which one of these cases you're going to fall into. All right. I hope you remembered that stuff about R values I just told you. Let's try and rank these in order from largest absolute value of R to the smallest one. So like most straight linitude to least straight linitude. This is 1, 1, 2, 3. Which one looks like the most close to a straight line? It's like the largest R. 1. Which one looks like the least close to a straight line? 2. Yeah, exactly. Perfect. Okay, this is a bunch of words, but just gonna talk through it really quick. So stuff you need to look out for when doing curve fitting. This is like a little bit less applicable to the stuff we've done so far, but you always need to make sure you look out for overfitting, which is that your model equation works super well for the data set that you have already. But if you want to predict y for unknown x values, then it would do a really bad job. Let's go back to this toy data that I made. Oh my God, I hate when the zoom controls come up and not ready. Go away. So if you look at this, I could fit a polynomial to this where the equation looks like this. And that would fit perfectly, 0 error, gorgeous fit, looks terrible. And if I try to predict it for like the value of 11, you'd probably throw it like all the way into the ceiling because I gave it a polynomial with like 20 parameters. So while that would be a valid curve fit, because I fit a curve to the data and it passes through all the points, so like ideally, it's great. It wouldn't work for any value that isn't on here because it's just so specific to this data set. Like when you look at this, you're like, oh, it's a straight line. But I could fit any equations to this that I want. So it's important to make sure that your equations are not too complicated for the situation that you're looking at. At the same time, try not to make sure it's too simple. Like we saw the parabola earlier. I could fit a straight line to that. It would be a very bad fit. So in this case, it would be also bad because it's missing the important trends in the data. Like the parabola example before, try not to apply linear models to nonlinear sets. So I mentioned the residual plots here. Residual plot is the plot of the errors only. So basically I fit a line to it, and then I look at the errors between the points in the line, and then I only plot those. So this type of plot helps like magnify the errors present in the data and helps bring out patterns that are kind of difficult to see. If the residual plot has any kind of pattern, linear regression is probably not the way to go. A good residual plot will look like a cloud. It'll look like this one. This actually is a residual plot. This is what it should look like. If you see this in your residual plot, don't use linear model. Bad, very bad. Here's some examples of residual plots. I realize these are kind of small, but these both look like straight lines, right? This one looks like a really nice straight line. This is kind of like also like a pretty good straight line. And I plot the errors, they look like a cloud. That's really good. That means the linear model is pretty appropriate. In this case, this looks like a straight line. When I measure the errors, it actually looks like a parabola, which means that linear model probably isn't the best idea. And if we look at this a little bit closer, it does seem like there's some kind of like scoop shoot going on, but it's kind of hard to see unless you already knew it was there. These are where I got these pictures from and also the internet. But if you want to read more about curve fitting, statistics, data 8's great, and then data 140 is like a little bit more rigorous. That's all I have. So any questions? Yeah.
That residual plot, is that just like what your graph looks like when you zoom in? Like,
Yeah, basically. So the residual plot is kind of like you take your straight line, like it's like this.
Yeah.
And then you joint it like this.
Yeah.
And then you stretch out all the errors.
Okay.
That's basically what it does. Any other questions? Okay, well, that's all I have. So feel free to head out a little early. And remember to go vote. Exercise your civil rights. And I'll see you guys on Thursday because I'm going to be here too. Sorry.